Okay, hello everybody. This is exam 2 from fall 2022 for MA 262. Just to preface, this is a pretty linear heavy exam, so I will try my best to explain concepts as well as work through these questions as we go along. But let's just get started. So in question 1, we're given this matrix 4 by 4, and we are asked to find which of the following sets is a basis of the column space of A. So let's talk about some of these terms first. So the column space of a matrix, we're going to denote that as column of A, right? It's the set of all possible linear combinations of its column vectors. And a basis for the column space is going to be, actually, I'll just write everything down as I go. So this is going to be equal to, or the definition of this rather is set of all possible linear combinations of column vectors. And then what is a basis, right? Basis is going to be the basis of a column space is going to be set of linearly independent vectors. Set of linearly independent vectors that span the column space of A. Right. So those are the two biggest concepts you really need to understand here. And the standard method we're going to use is just to identify the pivot columns of the matrix. How do you identify the pivot columns? Obviously, you have to go ahead and RREF this. It looks like a lot just because it's 4 by 4, but really there are some not too bad steps that are taken here, really. Um, but yeah, let's just get into it. So this we have our original matrix A. I'm gonna first get rid of this -1 right here, right? Just get this -1 right here. And the way I can do that is by saying that I'm going to say R2 is going to be equal to R2 plus R1. 1, -3, 0, -5. This becomes 0. R2 plus R1, right? So 4 minus 3 is 1. 1 plus 0 is 1. 7 minus 5 is 2. And the rest of our columns, or rows rather, sorry, stay the same. All right, so we have 1, 0 there. And realistically, you just want to keep getting as many zeros as possible. Next thing we're going to do is I can say R3 is equal to R3 minus 2 times R1. Why am I doing that? I can get rid of this 2 over here if I do that. So first I'll write down my first operation that I did. I said R2 was equal to R2 plus R1. This is from original matrix. Right. This is from the original matrix. Let's keep going. I said I want to do R3 is equal to R3 minus 2 R1. So our first two rows are going to stay the same. Right. But now R3 is equal to 2 times R1. So 2 minus 2 is 0. You know, that's what we were aiming for. 1 minus -6 is going to be 7. It's going to be 7. 7 minus 0 is just 0. And 4 minus 10 is going to be equal to -6. And then this stays the same. Because, and then this one, I said R3 is I'll put it here. R R3 is R3 minus 2R1, right? Let's keep going with this REF here. And now I can say R4 is going to be R4 plus 2R1. Why? Now I can, we can actually get rid of a lot here. But mainly I'm looking at this -2. And if I do R4 plus 2 rho 1, that becomes a 0. So again, all our rows except for R4 will stay the same. This becomes a 0, right? That's what we're looking for. 2 minus 6 is -4. This just stays as -4, and then 2 minus 8 is -8. And another extra step I'm going to take here is, no, I'll do that later. So R4 becomes R4 plus 2 rho 1. Right, so this is what we have right now. Oh, I'm sorry. I dropped a 7 here. This should stay as a 7. Right? And let me double check the rest of my work. And this should be a 14. Yeah. Because 4 minus -10 is 4 plus 10, which is 14. Yeah, my apologies. But I think the rest of this should be good. Yeah, this looks good. Okay. So, we're looking pretty good. Let's just keep going. And actually, just by inspection here, we can see that, I can divide row 3 by 7. I can divide row 2 by -4, right? So let's do that. 0, 1, 1, 2, 0, 1, 1, 2. Right. This is row 3 divided by 7. This is row 4 divided by 4. What do we notice? Our row 2 is 0, 1, 1, 2, which means these two bottom rows can all just go to 0, right? So I'll write this over here. 1 minus 3, 0, -5, 0, 1, 1, 2. And then bottom two rows are all zeros because we do row 3 minus row 2 and then row 4 minus row 2. I'll label all my operations here. Perfect. We have REF'd our matrix. Now we can easily find the answer from here. How are we going to do that? So our pivots are in our first two rows, right? Because those are where our leading ones are. These are our pivots. Now, the pivot positions are in the first and second columns, first and second columns. So the first and second columns of the original matrix A is going to form the basis for the column space. So what are the first two original columns here? We have 1, -1, 2, -2, and -3, 4, 1, -2. So therefore, the answer is B. So again, very important to realize, once you REF your matrix and you find your pivots, they're not, and they want you to find the basis of your column space. Do not use your REF columns. The columns of the original matrix A will form a basis for its column space. That is a very important thing to keep in mind. And honestly, that's something you could even see on the true or false, or the conceptual questions. But let's move on to question 2 now. This actually uses the same matrix from question 1. So if you were, you're using the timestamp on boiler exams and you're just tuning into this question, go back to question 1 to see how I REF this matrix. but the full REF version of this matrix is net 1, -3, 0, -5, 0, 1, 1, 2, and then 2 rows of zeros. Again, if you're wondering how I got here, you can go back to question 1, and I fully worked that out. But yes, so this is REF now. And now the row space of matrix A, it's kind of the same concept here. The row space of A is the set of all linear combinations of its row vectors, and elementary row operations do not change the row space. That's important to remember. And so a basis of the row space can also be found by taking the non-zero rows from any row echelon form of A. Again, it can be any row echelon form, but because we REF'd it in question 1, we're going to stick with the REF in question 2. Again, our pivots here are the same. You know, still just the first two rows here. And so the non-zero rows of this matrix form a basis for row A. And here you'll notice we are actually taking the REF form, which is also important to consider, right? So the answer is going to be C, because, that's row 1, that's row 2. Or, I'm sorry, I just circled D. The answer is going to be C. But yeah, biggest thing to understand here is basis of column space, you take original columns, right? Basis of row space, you can take the REF'd rows. Question 3. So this is a true false type of question, probably the hardest kind of questions you'll see on any of your exams. But let's go through it. So which of the following are true? If the reduced row echelon form of a 3 by 5 matrix is that, then the dimension of the solution space for AX must be 3. Actually, I don't want to do it like this. Let me go over concepts first. So the dimension space, so the dimension of the solution space is also called the null space, because, in this case, AX equals 0. So it's also the null space. And this is going to be equal, so kind of like the dimension of this, the dimension of AX equals 0 is going to be equal to the number of free variables, right? Which is going to be free variables. How do you calculate free variables? It's going to be number of columns minus the rank of your matrix. In this case, it's going to be rank of A. This is how you can calculate the number of free variables you have. And the rank is going to be your pivot columns. Okay. The rank, it doesn't change under row ops. It's defined by the REF, right? Um, let's Yeah, okay. So I'll write that down as well, because two is mentioning rank. So rank does not oops, rank does not change with row ops. Very important to remember. Row ops, it is dependent on RREF form. Okay. And question, or option 3, it's talking if W is in the set of all vectors in the space R2 of the form x and x squared, then W is a subspace of R squared. What you have to know is a set is a subspace. So, subspace. So let's talk about subspaces. Subspace. What does it need to contain? It needs to have a few things. It needs to have a zero vector, right? It needs to have a zero vector. It needs to be closed under addition. needs to be closed under addition, and it needs to be closed under addition and scalar multiplication. So these are kind of the properties we need. So if you notice, I'm kind of going over concepts by each choice we have. You know, this option one talks about the solution space. So here I'm talking about, and okay, solution space, again, is solution space is equal to dimension of null space in this specific question. In this specific question, the solution space of AX equals 0 is equal to the dimension of the null space. Okay, and then if I'm looking at question or option 4, the set W, you know, T121 plus S100, where T and S are real numbers, is a subspace of R3. What you have to know here is that the span of a set of vectors in a vector space is always going to be a subspace of that vector space. Because these two vectors are spanned. Yeah, so span of vector space always a subspace of that vector space, right? And now let's go through these options one by one by looking at what we know. Right. So one is, what does one say? If the reduced echelon form of a 3 by 5 matrix is that, then the dimension of the solution space for AX must be 3. This is false. The pivot positions we have are in columns 1, 3, and 4. What did we say about the pivot columns? That is our rank of A. So our rank of A is equal to 3 because we have 3 pivot columns. The matrix has 5 columns, n is equal to 5. 5 total columns, right? So now the solution space of AX equals 0, as I mentioned earlier, is the number of columns minus your rank of A. So number of columns minus rank of A is equal to 2. So therefore, the solution space or the dimension of your null space is equal to 2. But here it says 3, so this is false. Right. Going on to 2. If two m by n matrices A and B have the same reduced row echelon form, then rank A is equal to rank B. This is true. The rank of a matrix is defined by as many pivot positions as it has in row echelon form, right? This is what I say here. So rank does not change with row ops. It's dependent on the REF form. If the REF of A and B are the same, that means it has the same pivot columns, right? So if it has the same pivot columns, you know rank A is equal to rank B. It's yeah, I mentioned that as part of question one is here. So rank A is the pivot columns, and again, pivot columns is completely dependent on the REF. So if the REF is the same, the pivot columns are the same, and therefore rank A is also the same. So two is true. All right, let's see. Um, we talk about zero vector. It has a zero vector, right? You know, if x is 0, the vector is 0. So the zero vector exists. However, it has to be closed under addition, right? And if we, and what I mean by closed under addition is like, if I have, it's easier for me to give you an example. So let's say I have x equals 1. That means our vector is 1, 1. Let's say I have x equals 2. Now my vector is 2, 4. And when we add these two vectors together, we get 3, 5, which means our new x value here, x is equal to 3, right? But if x is equal to 3, then our x squared here should be equal to 9. And x squared corresponds to to our second value. 9 is not equal to 5. 9 not equal to 5. And so this is what I mean by it's not closed under addition. The x squared relationship no longer holds true when I add two vectors of that sort together. So 3 is false. Let's look at 4. W is defined as that. It's so the T and the S, all that really means is that it's the set of all linear combinations of the vectors 1, 1, 2, or 1, 2, 1, and 1, 0, 0. Right. So, and that's the definition of span for those two vectors. And again, as I said earlier, the span of a vector space will always be a subspace of that vector space. So 4 is true. And you have, therefore, 1 and 1, 2, and 4 are true. So C is our answer. Or am I lying? No, 1 is not true. Sorry, I already said 1 is not true. 2 and 4 are true. So oh, A. That's the option I'm looking for. 2 and 4 are true. So A is our answer. Yeah, definitely a more conceptual question, definitely a harder question. But really it's just you have to know these relationships of like rank and dimension space and null space. And what makes a vector or what makes a subspace and what doesn't make a subspace, right? So that's the way to go about these kinds of questions. We have another one here, unfortunately, but this one is much easier than the last one because it's just again asking about rank and column space. So let's see. Rank of A is 4. This is false because this is false because it only has 3 columns or three leading ones, right? Because you have a leading one right here, you have a leading one right here, and you have a leading one right there. And that is only 3 of them. So we can say 1 is false. The dimension of the column space must be 4. Not true. We just said rank is equal to 3 because it has 3 leading ones. 3 leading ones. The dimension of the column space is equal to the rank of A. And rank of A is 3. So the dimension of our column space is also 3 and not 4. The dimension of our solution space is 4. Now this one is true. Why is it true? Because the way we can find this is by doing n minus rank of A. What is n? N is the number of columns we have. How many columns do we have? We have 1, 2, 3, 4, 5, 6, 7 columns. Rank of A is 3. 7 minus 3 is 4. So 3 is true. Basis for our row space of A is that. This one is pretty easy. All you have to do is see if these vectors match up with the leading with the vectors that the pivot positions are in. The pivot positions are in columns 1, 2, and 3. And these are the vectors you get. So this is also true. So solutions 3 and 4 are true. So therefore D is your correct answer. Yeah, so this one was much easier than the last question because we didn't have to deal with any subspace stuff. I would say subspaces and vector spaces and the relations those have to each other are definitely the trickier kind of questions that you'll see on these exams. But I hope that wasn't too bad. Okay, on to more linear. We need to find the values of k such that 2k negative 2 is a linear combination of these two vectors. What makes something a linear combination? Well, let's say you have some vector v. V has to be equal to c1 v1 plus c2 v2 all the way to however many vectors you have, cn vn, such that c1, c2, and all the way to cn are just scalars, and v1, v2, and vn are your vectors. So c1 in this case, we can say c1, we can augment with 1, or we can say 1, 2, negative 1. This can be our v1, and our v2 can be 1, 3. Okay. And we want this to be equal to 2k negative 2. If you expand this out, you realize you have a system. How can we solve a system? We can use augmented matrices. So our vectors are going to be column vectors in our system. So we can say 1, 2, negative 1, 1, 3, k, k, and we're going to augment it with the vector v, essentially. 2k negative 2. This is always how you will set up these kinds of problems. But yeah, actually, I kind of want to drill this, like, I want to drill this again, because they can ask you questions outside the scope of just this, where it could be something conceptual. Essentially, this vector v will be a linear combination of vectors v1, 2, all the way to n. If the scalars exists such that this property is held true. So c1, c2, and cn have to be, real numbers. They have to exist. This system that we've set up here has to be solvable in order for um, this vector v here, essentially is what I'm calling it, to be a linear combination of these two vectors v1 and v2. So I hope that makes sense to everyone. But other than that, we can just solve this pretty easily. Um, we see the one, -1 and the -1, and I see the 1 and the 2. So I'm gonna do, we're gonna do R2 is equal to R2 minus 2R1. R2, this is 0, this is 1, this is k minus 4, and this is still -1, k negative 2. So what did I just do? I just did R2 is equal to R2 minus 2R1. Oops. And now I'm gonna get rid of this -1 here as well. Basically, I'm just trying to simplify this matrix and um, get zeros. So I want to get rid of this -1. What am I going to do to do that? I'm just going to do R3 is equal to R3 plus R1. So again, we have 1, 1, 1, 2. Oops, sorry, I forgot my augmentation line here. This is a 0, this is a k minus 1, and this will be a 0. And here I did R3 is equal to R3 plus R1. Now, what do we have? Believe it or not, we actually want to eliminate this value of k. I only want one row of k's. I want this k gone. Or this k term gone, rather. How do I want this k term gone? I'm going to do R3 is going to be equal to R3 minus k plus 1 R2. You might be asking, why R2? Why not R1? There's a 1 right here as well. Well, I want the 0 to stay in place, right? Because with this 1 up here, and if I do any kind of roll up there, the 0 will go away, right? But the other thing I want is I want all the k's in the same line. I want I somehow want a relationship of this row and all the k's on this side. So the easiest way to do that is to make it R3 is equal to R3 minus k plus 1 R2. 1, 1, 2, 0, 1. Now this is going to be k minus 4 still, because we're changing the R3 row, right? 0, 0. I'll show you why that becomes 0 in a second. It's just some algebra. And this becomes minus k plus 1. Oh, minus 1 plus 1. Hold on. This is a plus 1. And this should be k minus 4. But yeah, basically what I did here was I said this new R3 is going to be equal to R3 minus k plus 1 R2. Why do I want that? Well, if this is a system, and let's just say we have variables a and b, right? Or actually, I don't know, this is C1, this is C2. What does our system look like? We have C1 plus C2 is equal to 2. We have C2 equals k minus 4. And now we have, again, bottom row zeros, 0 is equal to minus k plus 1, k minus 4. Well, this is just a factored quadratic, right? Like, if I tried to somehow solve this system right here, I can't do that. I don't know what C1 is, I don't know what C2 is, and I don't know what k is. So you have two equations with three variables, you can't solve that. But here, you have one equation with one variable, and that's just k. So, and that's what we're trying to solve for at the end of the day, right? Like, there's no reason for us to solve for C1 and C2 when the question is asking for k. But this is just a simple quadratic, and we get k is equal to minus 1 and k is equal to 4. So the answer is A. But yes, biggest thing to note for this question is you can make a linear combination when this condition is satisfied, such that your scalar C1, C2, all the way to Cn exist. You set up your matrices and vectors like this. You can augment them, and it'll always be this setup right here. And then as you keep going through your row ops, you want all your k's in one row in this, not all your k's in one row. You want your k's in one row where the rest of your row is all zeros, because then you can either get a simple quadratic or maybe even a linear equation where you can solve for everything. I hope that makes sense. Let's move on to the next question. We have finally moved on to some DiffyQ, which I hope will be a nice break for everyone. But let's keep going. They give you your characteristic polynomial, nice of them, and they just want us to find the generic solution of this differential equation. So what are our roots? We have r equals 1, -1, with a multiplicity of 2. And then this is some quadratic that I will solve later. You can't factor that, by the way, which is why they didn't factor it for us. But yes, some quadratic that I will solve later. Um, yeah, let's look at the first little bit we have right off the bat, right? We have r is equal to 1, so we're going to have a c1 e to the x term. Because this polynomial will be taking the form. I will actually write out the generic form, but it's going to take on the form c1 e to the rx plus c2 xe to the Rx plus, you keep going, generic form, CK x to the k minus 1 e to the Rx, where k is your multiplicity. In this case, I'll keep this consistent. K is your multiplicity, right? So let's look at this. You have R equals 1, so you have C1 e to the x. You have -1 plus C2 e to the negative x, but you have -1 two times. Since you have it twice with a multiplicity of 2, we are going to we're going to multiply this by x because we have two of them. Whenever you have as much as high as the multiplicity is, you're going to multiply that term of the multiplicity of x to the multiplicity minus 1. That's what this denotes right here. So for example, let's say I had some solution with a multiplicity of like, multiplicity of like 3, and let's say the root was like 2. It would be C1 e to the 2x plus C1 x e to the 2x plus C1 x squared e to the 2x. And I would stop here. Why? Because k is 3, so my highest power of x has to be k minus 1, which is 2. And I have that x squared here already. So a little example to hopefully show you how many times you have to multiply your terms by x to get an independent solution. But we're not done because we have this quadratic, sitting right here. So let's solve it. Not factorable, so we're going to use the quadratic formula. So r is going to be equal to minus b plus or minus b squared, which is 4 minus 4ac. And I could have told you that this was going to be an imaginary number because all our solutions have sines and cosines in them, all over 2a. This simplifies all the way down to 1 plus or minus I, right? And we know that the generic form for this, let's say you have a plus or minus bi, the generic form for this is always going to be, for example, it'll always be e to the ax times c cosine bx plus d sine bx. So that's always going to be the generic form. Here our a is 1 and our b is also 1. So for us, it's going to be e to the x times c4, because we already had c3, cosine of x plus c5 sine of x. No reason to put any x's here because nothing repeats, right? That being said, our solution is going to be option C. Matches up with what exactly we have written out here. Yeah. Okay, on to question 7. And we're back to the linear. Okay, but this is pretty easy. This just wants determinants, right? So we just have to find the determinants, add them, and then find the value of k. The nice thing about this, however, is there are lots of zeros here, and so we don't actually have to take that many determinants. But yeah, so let's just get going. One important thing I want everyone to remember is, let's say we have some matrix A, determinant of A is equal to the determinant of A transposed. And the reason this is important is because you can use cofactor expansion on either your columns or your rows. So if there are more zeros in a certain column than there are zeros in a certain row, you're going to want to use that column for your cofactor expansion rather than that row, right? So for the first matrix, we are going to use column 3 because that has 2 zeros in it, and that is more zeros than any other row or column in this matrix. And we want to make our lives easy. So how are we going to do this? I'm going to write out the generic summation form of this, and then we will go from there. I3 determines the ith row and third column. First element of I3 is 0. Second element is also 0. Third element is 1. Fourth element is 2. Um, and what are our C's? Cij is just going to be equal to -1 to the I plus j times m ij, where m is the matrix you get after your cofactor expansion. So let's look at this. These two terms obviously are just going to 0. So we really just have to evaluate these two terms. Right. And this is how we determine the sign on that specific term. So when we look at 1 right here, it's in the third row, third column. So -1 to the 3 plus 3 is 6, which is just even. But I will again just work this out. 1 times 1 times -1, 3 plus 3. What is this, what is this matrix? Well, it's going to be, what is it going to be? It's going to be 2, 1, 2. It's going to be 2, 1, 2, 0, 1, 2, and then 4, 2, 2. How I got that? You just go down and across. And then you just look at the, oh, sorry, no. You just look at what's left. But yes, that is how you would do that. And then keep going. Plus 2 times -1, 4 plus 3, because we're looking at the fourth row, third column. And then our new matrix here, which is 2, 1, 2, 0, 1, 2, and 4, 2, 2. And again, how I find it. So for example, this first M here, I cross out the third, and I cross out this. So cross this out, cross this out. You get two, as you can see, you get 2, 1, 2, 0, 1, 2, 4, 2, 2. Right? And then if I want to do the same thing, I go fourth row, still third column, 2, 1, 2, 0, 1, 2, and 4, 2, 2. I miswrote this. My apologies. This last row should be 2, 1, -1. 2, 1, -1. Right, because I cross this out. 2, 1, 2, 0, 1, 2, 2, 1, -1. Now let's find these determinants. Two 3x3 determinants. We're just gonna look at, because it's just 3x3, we're just gonna go first row and just go from there. So it's gonna be 2 times the determinant of 1, 2, 2, 2, right? Minus 1 times the determinant of 0, 2, 4, 2. And plus 2 times the determinant of 0, 1, 4, 0, 1, 4, 2. This all becomes 2 times 2 minus 4 minus 1 times 0 minus 8 plus 2 times 0 minus 4, which is equal to -4. And now let's do the same thing for our other matrix here. We have 2 times the determinant of 1, 2, 1, -1, right? Plus 1 times the determinant of 0, 2, 2, -1, 0, 2, 2, -1, plus 2 times the determinant of 0, 1, 2, 1. And this is going to be equal to 2 times -1 minus 2 minus 1 times 0 minus 4 plus 2 times 0 minus 2 equal to -6. Now you might think we're going to have to do all like a whole bunch of stuff again for the second matrix right here. But if you notice something, the second matrix is actually upper triangular. And if a matrix is upper triangular, we can say the determinant is the product of the diagonal, which is just 2k, right? So determinant of A, which is determinant of A, which comes out to be 8, right? Because yes, 8. Determinant of A comes out to be 8 when you add these together appropriately. Um, yeah, how you may ask? It's because this becomes 1 times 1 times -4 plus 2 times -1 of -6. This is equal to 8. So 8 plus 2k equals 0. K is equal to -4. Answer is E. I hope that makes sense. This is just really testing your knowledge on how you, if you know how to take a determinant or not. Um, Also, I guess if you see the shortcut of the upper triangular matrix, that would save you a lot of time. And even then, it wouldn't be too bad because as you can see, we do have the column and even the row of 2 zeros, so it wouldn't be too bad. However, still easier than writing it all out. That being said, let's keep moving to question 8. We want to find values of m such that y of x equals x to the m is a solution of this system. They've done a good amount of the work for us. We just kind of have to do the rest. So if we assume that y of x is a solution, my bad. If y of x is a solution, right? Um, let's just start taking derivatives, right? So y prime This is just going to be product rule and y double prime. That's what we're looking at here. We're going to sub these into the differential equation. So this becomes m times m minus 1, x to the m minus 2, plus x times m x to the m minus 1, minus 3 x to the m. We can simplify some terms, right? By, yes. Yeah, we can simplify some terms. So we can just say 2m times m minus 1 x to the m, because this and this can't, oops, these and these cancel, right? And this will cancel. Plus m x to the m minus 3x to the m is equal to 0. We know x is greater than 0 and x to the m. So x to the m has to be greater than 0, or rather cannot be equal to 0, not greater than 0. So we can just divide by x to the m on both sides, and we're left with 2m times m minus 1 plus m minus 3 equals 0. When we expand this out, we get 2m squared minus 2m plus m minus 3 equals 0. So 2m squared minus m minus 3 is equal to 0. We factor, we're left with an m times 2m minus 3 plus 2m minus 3 equal to 0. This is m plus 1, 2m minus 3 equal to 0. So m is equal to -1, or 3/2. And as we can see, that is b. Yeah, this was a pretty straightforward question, just a lot of algebra more than anything else, and a little bit of derivatives. But I would say one of the easier questions we've had on this exam so far. Um, yeah, let's keep moving. I think we're getting into the diffie-q section part of this exam now. Yeah, these last 3 questions are all diffie-q, which is not bad at all. Let x of t satisfy the initial value problem, x of 2 pi, then x of 2 pi, that is x of t, is evaluated at t equals 2 pi. So they're asking us what is x of 2 pi, and to find x of 2 pi, we need to find x first. Right, so, you know, characteristic polynomial, lambda squared plus 4 lambda plus 5 equals 0. I'll let you know right now, this is not factorable. They want us to find this, they want us to use the quadratic formula, and we were most likely going to get a complex numbers. Minus b plus or minus square root of b squared, 16 minus 4 times 1 times 5, all over 2a. Right. This all simplifies down to -2 plus or minus I. And as I mentioned earlier, this takes on the form of e to the minus 2x c1 cosine x plus c2 sine of x. This is actually bad math. You want these to be t's because this is x of t. Doesn't really matter, but for sake of consistency, I'm going to keep these t's. Yeah, let's apply initial conditions. Before we apply initial conditions, we need to find x prime of t. prime of t. So this is going to be a product rule. So we're going to say, you know, derivative of e to the minus 2t. So minus 2e to the minus 2t times, everything inside. Plus, e to the minus 2t. And the derivatives are everything on the inside, which is minus c1 sine t plus c2 cosine t. Right. And now we can start plugging in initial conditions. So x of 0, e to the 0 just becomes 1. Cosine of 0 is just 1. So 1 times c1, and then sine of 0 is just 0. This is equal to 1. So what do I have? I have c1 is equal to 1. Same thing here. X prime of 0, again, negative 2 times e to the 0 is just negative 2. c1 cosine 0 is just going to give me c1, and then sine 0 is just going to be 0 again, plus 1 times, now c1 goes to 0, right? Because sine of 0 is 0, and now I'm just left with c2. This is all equal to negative 2. So you have minus 2 c1 plus c2 is equal to negative 2, but we know that c1 is equal to negative 1, so c2 is equal to 0. So our actual x of t is equal to just cosine of t, e to the t cosine of t, because c2 goes to 0. Right. Yeah. Now they want us to find x of 2 pi. It's going to be e to the minus 4 pi, and then cosine of 2 pi is just 1. So the answer to this is B. Right. Again, pretty simple problem. Make sure you know that this is, a homogeneous ODE. We're going to use a characteristic polynomial. In a bad math kind of way, the amount of like the power of your lambda is just going to be how many tick marks are on your x. So squared, 2 tick marks. This is essentially lambda to the 1 tick mark. This is essentially lambda to the 0 tick marks. And then you can solve from there. This is asking us to use the method of undetermined coefficients. It's not too bad. It's just you have to keep track of all your terms more than anything else. How are we going to keep track of all our terms? Let's look at the right-hand side of this equation first, actually. So I will call this, just for the sake of like reference, g of x, right? And on this will be g1 of x, this will be g2 of x, and this will be g3 of x, just to keep everything straight. They really don't give you enough space for this problem, which is unlucky. But let's just go with what we have. Let's look at g1 of x first. So we can see it has like some form of x in it, or e to the x in it. So we know it has to be something of the flavor something of the flavor d1 e to the x plus d2 x e to the x, right? Oh, no, I lied. We don't want to do that. This can stay the same. We're going to solve the characteristic polynomial first. Lambda squared minus 2 lambda plus 1 is equal to 0. And this is actually a perfect square. So lambda is equal to 1 with a multiplicity of 2. So that means your homogeneous solution, y sub h of x, is going to be c1 e to the x plus c2 x e to the x. Yeah. And now we can look at our right-hand side. So let's look at G1. So again, it's a polynomial multiplied to the exponent e to the x. Polynomial of the first degree, right? So a generic polynomial of the first degree is going to be d1 plus d2 x times e to the x. If you notice, that looks a lot like our partial solution right here. And we don't want that because those would just end up combining and not giving us our full solution, right? So what can we do to fix it? Well, we're going to multiply by x squared. Why are we going to multiply by x squared? Because our homogeneous solution had a multiplicity of 2. So we're going to multiply this by x squared. So that's part of our solution. Now let's look at G2. Here you have a lot of things going on. You have a polynomial degree 1, you have an exponent, and you have sines and cosines. So we're just going to have to break it up. So polynomial of degree 1, e1 plus e2 to the x, e to the x sine x plus f1 plus f2 x. I'm going to move this over. Plus f1 f2 x cosine x. Where does the cosine come from? If we want to generically expand sine of x, we always have to say it's essentially like a sine x plus b cosine x. This is like the general expansion, and you have to do it because that's how you could generically write those a trig function. Um, yeah. So this is what we have so far, right? Um, you can see that this involves the roots. The characteristic roots of this would be something like r is equal to 1 plus or minus I. And this is not the root of the homogeneous characteristic equation, right? We got lambda is equal to 1 for that. So the roots here are different, and there is no need to multiply anything by x or anything of the x power because these will all be independent. And finally, let's look at G3. I'll do this up here. Here, the root is going to be r equals 2, right? R equal 2 is not a root of the homogeneous characteristic equation, so we don't have to multiply anything, and the generic form of this is just going to be, we can say c1 e to the 2x. And the way I chose my variables, I just, or my constants rather, I've been looking at the answer choices as I've been going along, and I've realized that, for e to the 2x, for example, they stuck with c1. And yeah, they stuck with c1 for e to the 2x. They stuck with d when we multiplied those together. And they stuck with f for that. And actually, yeah, yeah. I didn't talk about what the homogeneous solution because we are just looking for our particular solution, as you can see here. And the way we find our particular solution is we're just going to add up G1, 2, and 3. So G1, we said it was x squared, D1 plus D2x e to the x. This does not agree with that. This does not agree with that. This does not agree with that. Both of them. So C and D both have C1 e to the 2x, but we can see C is multiplying our e and f terms by an x squared that we do not need. So therefore, our correct answer is D. Okay, last question of this exam. To satisfy the initial value question, y of 1, so they're asking us what is y of 1, right? Excuse me, sorry. What is y of 1? Yeah, okay. So we can actually use the method we used for question 10 as well. So first let's solve, so let's look for a homogeneous solution first, right? Lambda squared minus lambda is equal to 0, so lambda is equal to 0. Or, oh, sorry, no tick marks. Lambda minus 1 is equal to 0, so lambda is equal to plus or minus 1. So your homogeneous solution aspect of this is C1 e to the x plus C2 e to the negative x. And now we have to look at our non-homogeneous term. I'm just going to call this g of x again. So g of x is equal to minus x squared, right? And the generic form it takes on is ax squared plus bx plus c, right? So therefore, we have to find a, b, and c. And the way we can find a, b, and c, obviously, is we know a is equal to, is we're going to have to plug it back into our solution. So this is y p x, our particular solution. So y sub p double prime, y sub p prime is going to be equal to 2ax plus b. And then double prime is just going to be 2a. Now let's substitute this back into our equation. So y double prime is 2a minus ax squared plus bx plus c is equal to minus x squared, right? So what do we have here? Once we combine like terms, you have minus ax squared minus bx plus our constants of 2a minus c. This is going to be equal to minus 1 x squared. I'll show you why I'm doing that in a second, plus 0x plus 0. So obviously you have negative a is equal to negative 1, so a is equal to 1. There's no x term, so b is going to be equal to 0. And 2a minus c is equal to 0, and a is equal to 1, so c is equal to 2. So you have your, generic form of this equation. So y particular becomes x squared plus 2. And how to find our full solution, we're going to add our homogeneous solution and our particular solution. It's worth mentioning I did not multiply the particular solution by any power of x because the roots, there was no overlap there. Our homogeneous was all e to the x's, e to the minus x's, and our g of x was just this higher order polynomial. So there's no overlap there. And now we need to use our initial conditions. to find our values of C. So y prime of x is equal to C1 e to the x minus C2 e to the minus x plus 2x, right? Y of 0 is C1 plus C2 plus 2. C1 plus C2 plus 2 is equal to 4, right? So we have here. So C1 plus C2 is equal to 2. And then our y prime of 0 is going to be equal to C1 minus C2 is equal to 0. Minus C2 is equal to 0. So C1 is equal to C2. So therefore, this is equal to 1. Right? And now we can find our actual y of x because we have everything. E to the x plus e to the minus x plus x squared plus 2. This is our actual solution. And now we want to find y of 1. So y of 1 equal to e to the x, or no, e to the 1 plus e to the minus 1 plus 1 plus 2. So your answer is A. And that is the full exam for exam 2 for MA 262 from fall of 2022. That's a lot of twos. I hope that was helpful. Good luck studying.